Going for lecture one, and what is that content that we are going to see in this is the syllabus that we have. So this is the content given by SPPU for unit 2. Theoretically they have given 6 hours. So what is the content is discretization of structure. You are familiar with discretization word. That is then 1D, 2D, 3D element meshing. So one of these elements we will revise that again. Element selection criteria. So this is the new thing that you are going to see here. Refining mesh, new. Effect of mesh density in critical region and use of symmetry. So this is the part that actually we are going to cover. And this in this part, one or two points are there which are asked in exam. But in element quality criteria, there are many things mostly asked in semester examination. So element quality criteria, Jacobian, aspect ratio, warpage, minimum and maximum angles, average element size, minimum length, skewness, tetra collapse, etc. So these are the terminology that is used in element quality, and there are some relations and definitions of that also. Then higher order element versus mesh refinement. So higher order element, we will see here in detail. You must know that, but again we are going to see that in detail. Geometry associate mesh quality, bolted and welded joint representation, mesh independent. So these are the points that are given according to syllabus. And as I said, I'm going to go through this all content again when I'll complete this unit. First, we'll go for the discretization and understanding that discretization in detail now. As I said, it may be possible that in this unit we are going to go for details instead of briefs that we have seen in the last unit. Now, suppose you can see this figure I'm showing on the screen in which A and B part is there. A and B part of these figures are of the same object. If you see the diagram, actual physical entity is having this type of curve, as you can see my cursor moving, right? This is the curve that we have here. Here it is flat again and then curve. If you see, you are in third year now. You must be learning the gears now, spur gears. So teeth of the gears have such type of shape. So instead of analyzing these teeth in this way, what I am going to do is I am going to make the steps in this way. Step 1, step 2, step 3, step 4. And I am going to deal that as a rectangle. Formulation of mathematical equation for such rectangular figures or standard figures is easy than the complicated figures. So therefore, this second B is case where the formulation and all will be very easy, and therefore the analysis can be achieved. So what I have done here is I discretized this whole body into small parts. There are 4 parts that I shown here, and if as I go on increasing the number of parts, this analogous physical body is going to be more nearer to the actual physical body as you go on increasing the number of steps, and each step we call it as an element. So if you increase the number of element, it is going to be very nearer to the actual body, and the disadvantage of that is it will take time for analysis. It is time consuming, so computational time will be more in that case. So this converting the physical body into smaller parts is called as discretization, and the other name that is used for that is meshing. So this unit is all about meshing techniques. Okay. So next is we will understand this discretization in words. So in finite element method, what I explained now is given in words in this particular slide. We'll go for discretization machine. In finite element method, the body is divided into finite number of smaller units known as elements. As I said, the process of dividing the body into finite number of elements is called as discretization or meshing. The meshing can be manual meshing or automatic meshing. You are going to learn this manual, automatic and all more during our practical session, because individually each of you have to go for meshing. The accuracy of approximation can be increased by increasing the number of elements, as I said. However, with increasing number of elements, the amount of computation will increase. Right? So, going for the various types of elements. So, these are the revision of that elements. This picture is again repeated in this session, because I shown this same picture during last time when I shown that types of element. Okay, so 1D element, 2D element, and 3D element. Whereas you can see here element shape. So they are first order and second order. So this order also relate to the polynomial equation. Polynomial equation will be of first order, and here the polynomial equation will have second order. That is x square will be there. Here it will be x only. So when it is x square, it comes out to be quadratic equation near about. So in this way, first order, second order elements are shown, and in the first order elements, when we increase the nodes, there will be second order. So as I said, this is the repetition. So we'll move forward. Types of elements in CAE. So we have seen that here we are going to see in detail. You know the types of element. Previous slide actually, what I shown is types of element. Here we will see that in detail. So here I am showing that 1D, 2D and 3D elements. Here you can see the names also. You just concentrate on names also, because names are always given in the analysis software. And when you want to select the element, so you have to recognize that type of element by the name, not by the shape. So you can see 1D element here, okay, 2 nodes, whereas 3 nodes 1D element is also used. We are going to see this 1D, 2D and 3D in detail. Then in 2D we have triangles and quadrilaterals. So triangle have 3 elements, 3 edges, and quadrilateral have 4 edges. So 3 noded and 4 noded are, can you see this is first order, first row, and this is second order. Here it is 6 noded, and here it is 8 noded. Whereas in 3D we have tetrahedrons, hexahedrons, and pentahedrons. The shape of that you can see here. This is the triangular surfaces which are merged together. They contains a volume inside. Same here, hexahedron 4. And here the triangle, here it is pyramid, triangular pyramid. Here it is triangular prism. If you remember the engineering graphic subject. Going for the nodes, here it has 4 nodes, 8 nodes, 6 nodes. Here it is 10 nodes, 20 nodes, and 15 nodes. So number of nodes actually decide the displacement nodal unknowns. More the nodal unknowns, more will be complications you will have for solutions. And more the number of nodes, more will be the shape functions. So you know that nodal unknown, what it means. You know that what it means by shape functions. Shape functions actually are equal to the number of nodes. If four nodes, four shape function, n1, n2, n3, n4, and so on. Can you imagine for this 20 nodes? Therefore, there will be 20 shape functions. They will have the relation of with coordinates and nodal unknowns, that is the natural coordinates. And then after you have to go for finding the value of any point inside with the help of that 20 uh, shape functions. Okay, so this is about the types of element in CAE, but I'm just starting with the easiest thing that we have actually seen in the last case. But we'll go for the details of that. How important is this element in case of FEA? Element plays a very lead role in this picture. Okay, so lead hero is element. So element is only the thing that is going to decide whether that output is going to be accurate or not. So accuracy of post processor depends on selection of elements for your criteria. If I go for in more details, 1D, 2D, 3D, and other elements that included here. Can you see other is also included? Huh? Now I'm going in details that when we have 1D, so what is the quality it has is in XYZ space coordinates or space dimensions. If you consider XYZ as a space dimensions, then X is much more greater than Y and Z. So we call that as 1D. So any element or any shape, any mechanical member which is having one of the dimension is very high compared with the two others, then 1D element must be the element to be selected. Okay. So what is the shape? Whereas second is we'll compare all first, then we'll go for other points one by one, right? So the second is two of the dimensions are very large, x and z or x and y in case of 2D. So it is a paper-like structure, plain paper. Whereas 3D will have all three dimensions nearby. Much greater is not there. Other means if you are going to represent the mass, huh, there will be point element inside or concentrated mass inside the body, and you have to show that. So I'm going to show that by such elements. That is also available in other section. If you are going to represent a spring, you are using a spring. So instead of making that spring and model, directly element is available which has the qualities of that spring. Damper. So damper also can be shown. I have a doubt whether you are familiar with this word damper or not, because that is there in the detail in dynamics of machinery final year subject. So damper is one of the element that is used for uh, act as a resistance for vibrations. Whenever some vibrations are to be reduced, to be decreased, then damper is used. So your suspensions, of a car, actually you used to work as a damper. So such dampers if are to be shown. Gap. Sometimes we have gap inside the body, ribs gaps that are to be shown, and rigid. So rigid body if is to be shown. Rigid body means any body which has negligible deformation after some load is applied on it. We call that as a rigid body. So it is not going to play any role inside that analysis. So how to show that rigid body? If any machine part or any machine member has that rigid part in it, then that can be shown by these other elements. So in rigid body, you have RBE2, RBE3, and so it is a rigid body element, to a rigid body element 3, and so on. And weld. So weld we are going to see in detail at the end of this unit, weld joint, because analysis of welded joints and all is a very critical part in analysis. So we'll see that in detail also. So we have other elements for representing welds also. So what is the element shape that we are going to use for 1D? It is line. Then element shape that we are going to use for 2D is chord, quadrilateral or triangle. Tri. We've seen that in the previous slide, quadrilateral triangle. And for 3D case, as we seen a tetrahedron, pentahedron, hexahedron, pyramidon, right? Then additional data from user. So this is a general thing that is actually we discussed. But even though the two dimensions are negligible, we need to give cross-sectional area in 1D case. Okay. Then here in this case, a thickness which we are considering as a negligible, that is to be given, and how that thickness is given and all we will see in details. Then in case of 3D, there is nothing to be given addition to the geometry, because all three dimensions, all three uh, space dimensions are actually demanded at the first only and given only. So what are the element type that can be used for that is rod, bar, beam, pipe, asymmetric shell, these type of parts. Okay, this type of element types can be used. So what is the meaning of this element type? So this will be the name that you will have written in the software when you are going to select the element. So you have to select rod, bar, beam, pipe like this for 1D case. Whereas a thin shell, plate, membrane, plane stress, plane strain, asymmetric solid, these are the names of the shells, or it is actually generally called as shell. uh, Whenever you are not going to get the accurate results, or otherwise the result output results are deviating from actual. Okay, actually the results are different, and cis suppose are giving the result with after analysis are very deviation, having a large error in between. In that case, the first job that is done is change of shell. What is the meaning of that? Change of shell is change of element. So these of elements that we are going to use 2D, and this solid is the name that you use here when you want to use 3D element. And what is the practical application of 1D element? So this also you see, so that whenever you are working in industry or somewhere and you need to use this ANSYS. So these are the practical applications. So at the time of when you are in the job, you must remember this practical application, so that at that time you will decide of your own which element to use. So when you are going to go for analysis of long shaft, beams, pin joints, connections, elements, etc., then you have to find this 1D as an element to be used. Then when it is sheet metal parts, plastic components like an instrument panel and all, like car covers, car bodies, bonnet, roof, doors cover of car if you go for automobiles. These all actually are a 2D element, can be preferred for them. And for 3D, transmission casing, engine block, crankshaft, solid elements, if you have to go for 3D elements to be used for. Now, if we'll proceed with this, so this is the details of elements that actually we seen in very brief in the first unit. And these details are also going to help you to answer the questions of first unit related to elements, because you know now in depth about the elements. More depth you will know in coming session, because it is the element that we are going to deal throughout this unit. So this is one of the diagram here I am using for showing the elements that can be used for the different shapes and sizes of any object. So this physical quantity, if is modeled inside the analysis, then the part at the bottom you can see is a plane surface. Therefore, 2D element can be preferred for that. This part which is holding that solid part, 1D element can be preferred for that, whereas 3D can be preferred for the top part which is a solid, and rigid case can be considered for this part. Anything like mass and all concentrated somewhere at its CG, actually concentrated at its center of gravity. So what is this CG and all? You revise that again. So this is the one of the guiding diagram actually, which you will guide you that how to select the element for different shapes of any mechanical object. So proceeding for the displacement function of 1D element. So if you remember, this is the slide that you are saying again. I discussed about the displacement function in the last case also, last unit also, previous sessions. But here, because we are going to use this again, therefore I'm just revising that again, and it is given in the points also in the syllabus. So generalized polynomial displacement function for 1D element is given here like this. You know that, and depending on number of nodes, this order is going to be decided. So up to 1 a1x it is first order, up to a2x square it is second order, up to a3x3 it is third order, and so on. So for displacement function for two node 1D element, as I said, 1D element and first order. So this will be the polynomial equation that we will use for that. This is the displacement I shown here. I discussed this in detail in the previous session. U1, U2 are the displacement of that two nodes, which actually we call as nodal unknowns. And if it is three node, then the polynomial equation changes to a0 a1x plus a2x square, and the displacement will be of three nodes, because we are going to consider the three node instead of two nodes. So these two diagrams as I shown here, one 2D node and two node and three node, are representing the elements of a same body, but the displacement in the first case you are getting two displacement at the two ends, and in between you have a straight line motion, whereas here you have curve. Actually, this type of element with three nodes instead of two will give you the detailed and actual displacement, right? So for more actual, you have to increase the number of nodes. So because this is actually completed in the previous session, so I am going forward for the next important point of this unit. And what that important point is, the terminology used in finite element analysis. So these are the 10 terminology that we are going to use during our unit, during our this finite element analysis, or during our whole subject, during our all 6 units. We will use this terminology again and again. So we need to understand this terminology in detail, and these all 10 terms, out of that many of the terms you heard in previous sessions also, and you actually know about that. So if such case will be there, I'll not go in detail. I'll just give the definition and I'll move forward. So the first terminology that we use is domain or continuum. The other word that is used for that is continuum. So when it is domain or continuum, so what is the meaning of that? Actually, it is the field or the structure, body structure, which we are going to call as a domain. Domain means what is that area in which you are working for, the area of your work. So in technical words, it is going to be called as in finite element method, the body structure or entire region under analysis is called as continuum or domain. Whenever there will be this name or this term that will be there discussed in the coming sessions, continuum or domain. The meaning of that will be this, that the region under analysis. This is general definition of that. So in our analysis, the body part, actually we are going to call as our domain, pole part. Then the second is element. So we are discussing this element from the first unit. In infinite element method, the body structure of continuum is divided into finite number of smaller units known as elements. You know that. I proceed. Nodes. You know. So element is made of nodes. So ends of that element or in between also you will have the nodes. So in finite element method, the elements are considered interconnected at joints. So this is a technical definition of that, where which are known as nodes or nodal points. So element means all whole structure of the body is divided into small parts, and for making it whole body, we need to connect that all elements small part to each other. Where they are connected to each other, we are going to call that part or that point as a node. It is only at nodes the continuity equations are required to be satisfied. So actually we are going to call or calculate that continuity equation or output of the result at the nodes, and that result actually displayed in the pre-post processor. Next is constraints. So this is the general word that is used for constraints, means resistances, the limitations, right? The finite element method, in finite element method, the constraint is complete prevention or partial restriction of movement at source. So that constraints that you have to give, that cannot be moved in the x and y direction, motion possible in z direction only. So x and y is constraint like this. So when this constraint word used, it means that we are preventing or resisting the motion or the degree of freedom in that particular direction. Next is loads. So actually we have not used load yet. We are just discussing for meshing, because after meshing we have to go for applying the loads on the body. So many type of load actually you will know, but the name that we are going to use in case of finite element analysis is somewhat different. What are the names that we are going to use? So the forces and movements that are acting inside the body, okay, in the continuum or in the domain, we are going to call them as the loads. But what are the types of loads that we will have here? Then there will be point load. This is one name that we use already, point loads. Body force. So body force is nothing but the concentrated force due to body, like concentrated mass, or therefore the weight will be acting from that mass. So we are going to call that as body force. And surface force or surface traction. So surface force is nothing but the distributed force, like uniformly distributed force, uniformly distributed along a line or uniformly distributed along a surface or uniformly distributed along the volume. It may be uniformly varying load also. So these are the loads actually you learn in solid mechanics. But here we are taking that all load UVL, UDL under this surface force only. So these are the names that we are going to use for nodes in ANSYS when we are going to apply that. Fifth term we are going through. We will try to complete that. 8 minutes are there. Anyway, sixth is degrees of freedom. So degrees of freedom is one of the term that you know actually that the in general degrees of freedom is the possibilities of motion. So it is done in technical words. It says that it is the number of independent coordinates which must be specified to uniquely define all the displacements. Independent, these words and their meaning are very important. Independent coordinates. Independent means if suppose there are two coordinates x and y, motion is possible, but x depends on y. So we cannot call that as the two degrees of freedom because they are not independent. So therefore, the coordinates which are having motion, they must be independent of each other, and then only we can count them individually. So in this way, independent coordinates, if you count that, that will be the number of degree of freedom. Then discretization. So no need, I think, to discuss that again, which we already see. Then we'll go for eighth, order of element. So this is also one of the things that we must understand. We see that already, but we will again understand that from this point of view. The displacement function of an element is represented by polynomial. So the order of that polynomial is going to be order of element, right? If you go for generalized equation, then this is the generalized equation that we have. Depending on the first order, this will have the first order element will have this equation that will be used for solution. We will use that, don't worry. And displacement function for second order element, you will use this. Second order means x square, only x first order. Third order, x cube, and so on. So for order case, we will have this diagram to understand the first order and second order element. Can you see? I am showing this diagram again, third time. And now in the third time, you have to look at this diagram by some other perspective. Getting my point? Okay. So element shape here, last two columns you can see first order elements, second order elements. You have seen the equation that can be used for the first order and second order. So after order, we will go for, we will complete all that tail so that we can move for the next topic in the next session. External and internal nodes. So what is the meaning of that? The nodes which are at the corners of the element are called as external nodes, whereas the nodes which are within the elements are called as internal nodes. Can you see one diagram I am showing here? Two nodes, 1 and 2 are external nodes, and 3 is internal nodes because it is inside within the element. Similarly, for the 3 triangular case, internal node is going to be 4, whereas 1, 2, 3 are going to be external nodes. In case of pyramid or tetrahedron, you can see that 1, 2, 3, 4 are actually external nodes and 5 is internal node. Okay. So why I'm discussing this terminology? Because we are going to use this term in the coming sessions. So at that time, you must understand what I am talking about. I'm going to call that there are two internal nodes which are going to this and that. You must understand what is the meaning of internal node, external node, degree of freedom, order of element, discretization, degree of freedom, load, constraint, like that. So last 10th that we'll see, and we'll go for attendance. So primary and secondary variables. So is it required to discuss that again? Because these are the variable that we see. Primary variable means the variable that you are going to directly get from the displacement, nodal unknowns. From nodal unknown, directly you will get that variable. So then after using that variable, you have to derive the other variables. So direct variable, whatever you are getting is primary, and the derived variable then after are going to be called as secondary.